Berkeley, was considering coming here, but somehow the weather was better there. Anyway, but she ended up a PhD there with Ms. Zarani. Then she was also a postdoc at both IAS and Microsoft Redmond. And but I should tell you something about her. She also has another, besides doing research, she's also known for surfing. I think she does not go out surfing these days without having 3 boards in her quiver. And so anyway, she surfed all over the world. So she's very famous for that also. But anyway, Alexandra, it's all yours.
I'm actually in a surf movie. I'm not kidding. It's a documentary. I'm in a surf documentary.
What's it called?
It Ain't Pretty. I can show you after. It's on iTunes, you can see it. I'm not the main character, but you know, but I do surf in the movie, so technically, like, I am more famous at surfing than. Yeah. Okay. So fine. All right. So this is recent work, both written up and some open stuff, ongoing research with 2 of my students, Charles and Xian, and another faculty person at UC Karthik. I'm going to talk about matrix signings, which is not matrix signatures, as some people had confused. It's just plain old signs, 0, +1, -1. And what do they imply in constructing expander graphs and finding perfect 2 matchings in graphs? So first of all, I am assuming everybody here is familiar with graph spectra, but let me give you the 2-minute sort of spiel of why you should care about spectral graphs and what they are. So spectral graphs are important for many applications. So no matter what area of computer science you come from, you have probably seen, even if you don't know it, a spectral algorithm. So if you're doing image segmentation, spectra are used to separate, images from the background, or the bear or something. Is that a bear? Yeah. From the background. If you ever used Google to search something, so you type something on Google search box, the way it sorts the results in order that come up, for your search are done by a spectral algorithm that's called Google PageRank. If you're a doctor or you work with doctors and you want to take a medical scan like an MRI, represent it as a graph in some 2D, let's say, and find clusters in this graph, which means I need to detect points that are more connected within each other than with the outside points. In this example, there's this inside cluster that I have cycled that would represent an anomaly like a tumor. So you could use spectral algorithms to find clusters like that and detect tumors if you don't want to go through the scans by yourself. So spectral graphs are great. It's the bottom line of this. But what are they? So here's a graph. And clearly, you can represent this graph in Algorithms 101 course. You learned you can represent this graph as an adjacency matrix. There are other ways to represent it, but this is one popular one where it's an n by n matrix. It's symmetric, and it has entry ij equal to wij, the weight of the edge ij, or 1 if the graph is unweighted, and 0 otherwise. So this is just the immediate representation of the graph, and it's obvious that you can do that. However, what's not so obvious is that this is a matrix. So you can forget about the graph and just deal with the matrix. So it's a linear operator. It can be used to multiply vectors. And there are some special vectors that don't rotate, but just scale. So ax equals lambda x. X is an eigenvector. Lambda is an eigenvalue. And for adjacency matrices, I will refer to the spectrum as the set of n eigenvalues. They could be multiplicities, ordered in decreasing order, typically. Decreasing order of magnitude, so lambda 1 through lambda n. Okay, so this is what graph spectra are, and the way I like to see graph spectra is with one analogy that might seem a bit cheesy to a lot of you, but bear with me. So, let's say you're playing a musical instrument, you're playing the guitar or a drum, and you want to go to the store, to the music store, and buy a new guitar. And you're interested in how it sounds and if the sound will fit your needs, like the music you want to play. You can do that by going to the store and seeing what the shape of the guitar is, what the dimensions of the guitar are, what the wood what it's made from, how the strings look like, and all of those features. But unless you play it, there's no way to understand the guitar like you would like to. So the eigenvalues of graphs are what the sound is for musical instruments. So they're the sound of graphs in my world. So other than the fact that you understand graphs by their sound, just like you understand guitars by their sound, there is a really important reason why a lot of computer science cares about graph spectrum. And this has to do with something I already mentioned before, clustering or cutting. So we say that a graph is not well connected if it's easily cut in two pieces, like this example. And sparse cuts are important to know if they exist and what they are for many reasons. So for example, you want to build a network. You want to design a network topology to serve some purpose to maximize throughput of your network. But you want the network to be fault tolerant. So you don't really want the network to look like that, because if a link fails with some probability, there is some probability that this middle link fails, and then two big pieces of the network become disconnected. So you really need to know if your network topology has a sparse cut. Otherwise, it's a bad design. Or if you want to build roads, you really don't want to have two cities connected with only one bridge, because if there's a traffic jam, there's no way for people to commute back and forth. So you really want road networks and internet networks and all of the networks pretty much to be well connected. Or you might want to do community detection for personalized advertising on Facebook that translates to finding some kind of clustering, some kind of sparse cut. So you either want to find a sparse cut or you want to know that none exists. Either way, finding sparse cuts or knowing that none exist are important, is important for a lot of computer science applications. So what is a sparse cut? We look at the ratio. You look at the partition of the graph into a set S and the complement S prime. These are sets of nodes. We care about the ratio of the edges crossing the cut that go between S and S prime over the size of the smallest, or over the size of the smallest side of the cut. So this is what we call a cut, or a cut ratio. And you will notice that this makes a bit more sense than, let's say, looking at the min cut for the applications I mentioned. Min cut is the one that you don't care about the ratio, you just care about the number of edges crossing the cut, because it takes into account the fact that the cut needs to be somewhat balanced. So you really don't care about outliers that much in this definition. You care about not having any cuts that separate big pieces of the network. And the sparsest cut is just defined to be the minimum over all partitions, S and S complement of this ratio. So for all the reasons I mentioned, finding sparsest cut in a graph is important, and in this case, it's easy to see what the sparsest cut is. However, this is one of the notorious NP-hard problems. So unless P is equal to NP, we don't hope for a polynomial-time algorithm to solve this problem, which we actually want to solve in practice a lot of the times. And here is where graph spectra comes about. There's this famous inequality that started by Cheeger. It was about manifolds, inequality on manifolds, and then got translated to discrete structures by Alon, Millman, and Spencer. That is still known by Cheeger's inequality. And it says, okay, finding the sparsest cut is NP-hard. However, if you just look at the second eigenvalue of the adjacency matrix of your graph, in other words, if you just look at the first eigenvalue, which is always D for D regular graphs, minus the second eigenvalue, the spectral gap, as we call it, this is a pretty good approximation of the sparse cut. So this is about deregular graphs. It generalizes to non-deregular graphs, but it's prettier to talk about deregular graphs, so let's just talk about that. So Cheeger's inequality says that eigenvalues give you what you want up to some approximation. So for most practical purposes, and in fact a lot of the spectral algorithms that I've mentioned before, with image segmentation, et cetera, use this spectral technique. This translates to an algorithm as well. It's not just an inequality to find a cut that's pretty close to the sparse cut. Okay, so this is an important reason why we care about graph spectra. So now this talk is about signings. Let's see, where do signings come in? So here is a graph, the Facebook, or not the whole Facebook graph, but some part of the Facebook graph. And you know, graphs can be used to represent social networks, for example. There is an edge between A and B, if A and B are friends with each other. And it looks like this. There's an adjacency matrix that represents this, the Facebook graph. And however, notice that we can only talk about are A and B friends with each other or not. Let's say A and B are friends on Facebook, but A dislikes B. They have different political views, so there is absolutely no way, you know, for them to be friends, like, which I strongly believe these days. So how do, seriously, at least if you talk about it loudly, I mean, you might be able to be friends if you're silent, but you know, there's absolutely no way otherwise. But how do you capture this fact? How do you capture the fact that A and B dislike each other, or they're different, or they don't cooperate, or whatever negative connotation you want to assign with this? Well, you can capture it with the signed adjacency matrix, where if A and B dislike each other, you put a -1 instead of a 1. And this is just, you know, that's the main player of this talk is a signed adjacency matrix that looks like that. Okay? So this is the tools and the ideas that I'm going to present results about. So here's the first thing, the first result. It has to do with these signings, the signed adjacency matrices, and building expander graphs.
Can I ask you a question?
Yes.
Cheeger is probably relative for a degree D graph, so a regular graph.
Yes. As I presented it, but there is a version for any degree. Yeah.
But you're not going to restrict yourself in this talk to regular graphs.
Well, for this part of the talk, I am, because the definition includes the deregular, you'll see, but not in general, yes.
Okay. Is there a Cheeger inequality for sign graphs?
No. So I mean, as we will, let me explain what I have to say, and then we will see easily that this is not the case. They represent something different. Okay, so let's go back to cutting and all these wonderful things that you know, having reliable fault-tolerant networks can do to us. The question is, are there even graphs that have no sparse cuts? And the answer is, of course they are. Don't be silly. You take the complete graph and you connect every node to every other node. And here's a graph with no sparse cuts. No matter where you cut it, it's a great cut. It's the best you can do. However, the complete graph is very expensive for any network topology. So we're really interested in expander graphs, as we call them, that are graphs that are almost tree-like. They have very, very few edges. They have linear number of edges. So the complete graph has quadratic number of edges. So they're as sparse as it gets, but still have the same behavior in terms of cutting as the complete graph. Those are called expander graphs. And for all the reasons I mentioned, including probability amplification, error correcting codes, and a million others, let's not spend the whole talk telling you why expanders are wonderful. They're really useful to know how to construct. And it turned out that this dual view of expansion that relates eigenvalues with the cut property helped researchers construct expander graphs. So here is a sort of reminder of what the situation is. We have these n eigenvalues listed in decreasing order of magnitude. And for deregular graph, the first eigenvalue is always d. So let's forget about that, because a graph's expander, non-expander, disconnected, or connected would always have a first eigenvalue d if they are deregular. And let's look at the second largest eigenvalue in magnitude, lambda 2. Most of the cases of interest, the lambda 2 is actually the second eigenvalue in magnitude. This is not always the case, but let's pretend that it is right now. And d minus lambda 2 is called the spectral gap. And we saw that the spectral gap determines the expansion. So the larger the spectral gap is, or in other words, the smaller lambda 2 is, the furthest away lambda 2 is from d, the better expander the graph is. So expansion is good. Spectral gap leads to good expansion. So how much gap can we get? If we have a deregular graph, and you can think of d as 3 or 5 or something small, as I said, they're very sparse graphs that simulate, approximate the complete graph. How much spectral gap can we get? Can it get 0? Can it get arbitrarily small? Can it get negative? Or lambda 2, I mean, can it get negative? And there's this theorem by Alon and Bopana that it says no matter what graph I take, if my graph is deregular, lambda 2 has to be bigger than 2 root d minus 1. So the best spectral gap I can hope for is d minus 2 root d minus 1. Okay, so graphs that achieve this gap are called Ramanujan graphs. Doesn't matter why. If you've seen the movie about this Indian mathematician, maybe you'll know why. But there's this Indian mathematician that the name goes, it's for him. And the question is, okay, we know that this is the bound that we have, but do they actually exist? And if they do, can we construct them? These are the optimal expanders, so we want to construct the optimal expanders. Can we do that? The first question is, do they exist? And okay, it's easy to say they exist for d plus 1 nodes. A complete graph on d plus 1 nodes is a deregular graph that's a Ramanujan expander. But we really care about creating arbitrary large families of Ramanujan graphs. And this was a celebrated result by Lubotsky, Phillips, and Sarnak, that they indeed showed that such graphs exist. And they gave a polynomial-time construction for them. However, they were only able to prove, plus extensions by other people that I haven't named there, that we can do that only if d minus 1 is some prime power. So realistically, you would never say, okay, I want to construct an optimal expander network, but the constraint is that the degree is a prime power. This doesn't happen. So you really need to understand whether or not Ramanujan graphs exist for all degrees. For that purpose, Joel Freeman suggested how to build those things via what we call lifts. So here's how this process would go. You start with a small Ramanujan expander, complete graph, let's say on d plus 1 nodes, and you take a lift, which I'll say what it is in a second, and repeat. So lifting multiplies the number of nodes in the graph by whatever degree of the lift you take, by 2, by 3, it doesn't matter, arbitrarily so. So then, like that, you would keep building progressively larger graphs. And if this lifting operation preserves the second eigenvalue, because you started with something good, so as long as you preserve the second eigenvalue, the new graph has bounded second eigenvalue, but 2 root d minus 1, then this would give you arbitrarily large families of Ramanujan expanders of all degrees, because you could start with k d plus 1 for any d. So here's what lifts are. Some of you might have seen them as graph covers. If you ever worked on unique games conjecture, this is the label extended graph. There's many reasons why people would have worked on those things. So you just start with a graph, let's say the triangle graph, and replace every vertex with k vertices. For whatever k I take, I call this a k lift. So this is a 3 lift. You have every vertex replaced by 3 vertices. And then every edge that existed in the original graph is replaced by a matching, or a permutation, an element of Sk, the symmetric group of k elements. So there are many choices to take that matching, as you see. Both of them are 3 lifts of the base graph, but they are different graphs. One is disconnected, the other is not. So here I choose what I call the identity permutation, where the first copy of every node gets matched to the first copy of the other node, etc. And here is some other permutation. So this is what lifts are. And depending on how I choose this lift, the spectrum of this resulting graph is very different, as you can see. One is disconnected, so the expansion would be 0, would be a cut that cuts no edges. And some other might be a good expander. Okay, so one important observation is that no matter what you do by lifting, the eigenvalues of the original graph are also eigenvalues of the lift. So you cannot get away from what you started with. You need to start with a Ramanujan expander in order to hope to get a Ramanujan expander. And all you need to do for this iterative lifting process that Freeman suggested to construct arbitrarily large Ramanujan graphs is to make sure that the rest, or the new eigenvalues of the lift, are bounded, hopefully by the Ramanujan bound. There's a recent result by Marcus Pillman and Srivastava, I guess not so recent anymore, but nonetheless very important result, that showed that for every graph, there always exists a 2 lift, where you only multiply the number of nodes by 2, or a 2 cover, that achieves the Ramanujan bound. So all the new eigenvalues are bounded by 2 root d minus 1. Their proof was existential, so we still, yes?
For every graph or every Ramanujan graph?
Well, this is for every graph, but you only care about the new eigenvalues. So yeah, if the original graph was disconnected, you still get a disconnected graph because of the old eigenvalues, but the new eigenvalues are bounded. So yeah. So this result is not constructive, unfortunately, and it's a probabilistic method style argument. So we still don't know how to construct expander graphs. So now let's go back to signings. Remember I talked about the sign adjacency matrix. So now here is a 2 lift of an edge. For every edge I have 2 choices. I can either lift it with the identity permutation or the cross permutation. There's no other choice if my degree of the lift is 2. So now I can see this as a signing of the edges of the graph. If I choose the identity permutation, I just leave the entry of the adjacency matrix as is. If I choose the cross permutation, I multiply it by -1. So this is exactly the sign, from this lifting process, I can get exactly a signed adjacency matrix. According to what choice of the matchings I have, I get a different signed adjacency matrix. And it turns out, by an easy observation, that the eigenvalues of the lifted graph, of the bigger graph, are equal to the union of the eigenvalues of the original graph and the eigenvalues of the signed adjacency matrix. So now lifting becomes, or finding a lift that's Ramanujan, we know one exists, becomes a question of making sure the largest eigenvalue of the signed adjacency matrix is bounded by 2 root d minus 1. So this is exactly our task. Okay, so for many long time, maybe 3 years even, the same collaborators and I tried to prove or to design an algorithm to find a signing that bounds the maximum eigenvalue of the signed adjacency matrix by 2 root d minus 1. And let's ask a more general problem. So I give you any real symmetric n by n matrix and any real number lambda. I want to verify that there exists a signing of the matrix such that the maximum eigenvalue of the signed matrix is bounded by lambda. It's at most lambda. So if we knew how to solve this problem, and if we knew how to solve it algorithmically moreover, we would be able to also, as a special case, find the signing of an adjacency matrix that bounds, and lambda would be 2 root d minus 1. So a polynomial algorithm for this problem would imply immediately a polynomial-time algorithm to construct Ramanujan expanders of all degrees. So the first thing we show in this work is that this problem is NP-hard, which is very unfortunate, but interesting nonetheless. At least it gives us some idea why all researchers, and there are many of them, that work on constructing Ramanujan graphs have failed. It doesn't say that you cannot find the polynomial-time algorithm to do it. It just says you cannot do it with a general algorithm for this problem.
It's really about finding bipartite Ramanujan graphs or any?
Right, yes. I mean, if you want to bound both eigenvalues. And the reduction actually, it goes from a problem called partition, which is pretty standard NP-hard problem, and you're given a vector B, and you want to just assign plus and minus 1 in front of the element so that the sum is 0. So hopefully everybody knows partition, but if you don't, this is what it is. So from that, we construct this matrix M. That's self-explanatory. I'm just giving you a quick idea. And we prove that this matrix is positive semi-definite if and only if there is a way to partition B. And from that, you can see how the bounding by lambda eigenvalue problem would be proven to be NP-hard. So this is the reduction idea for this problem. And if there are no more questions on expanders, I want to move to the second part.
So what happens if you take a random lift of
yeah, so this is another paper of ours, actually. And many other people, so it depends what you mean by random lift. Do you mean two lift?
Random matchings.
Two lift, or general?
Or an arbitrary, so you take your, say your KD plus 1, and you take n by n, and you put n, and you say pile n
But each
So a large lift.
large lift. And
Yeah,
you
so-
take a random matching on each of them.
Yeah, so if you have a random matching from the symmetric group of size k for arbitrary k going to infinity, then a random lift has eigenvalue 2 root d minus 1 plus 1 with high probability. This is a result, I think the optimal result is due to Putter, but there is a lot of Van Wu and Joel Friedman and stuff. If you take a random 2 lift or a random k lift, where k is chosen from a cyclic group, so only shift lifts, then we have a result where this lift is constant away. So the eigenvalues with high probability, some constant root d minus 1, as long as k is small enough. Once you take a shift lift where k is arbitrarily large, or larger than 2 to the n over d squared, then there's no lift that's even constant expanding. So with shift lifts and 2 lifts, things are kind of tricky. With general lifts, the proofs are trace method. I mean, trace method works to give you some expansion, and then you have other bounds. Okay.
I should have asked this before, but what is a Ramanujan graph?
The one that achieves the Alon-Bopana bound for the second eigenvalue. So we said that by Alon-Bopana.
Oh, and that was constructed in a non.
No, I mean, this is just a
way.
proof.
Proved to exist in a non-constructed way, right? Okay.
Let me find it quickly. Yeah, so we said, okay, we want the irregular graphs, d equals 3 or 5 or something small, because we want them to be sparse. And we want to make lambda 2 as small as possible, because d minus lambda 2 determines the expansion. So the bigger d minus lambda 2 is, or the smaller lambda 2 is, the better expander the graph. So how small lambda 2 can be determines how good of an expander can something be, but lambda 2 can never be smaller than 2 to the minus 1. And if you achieve this bound, the graph is called Ramanujan. So graphs that achieve this are called Ramanujan. Okay, so the second part has to do with perfect 2 matchings and perfect matchings as well in bipartite graphs. Perfect 2 matchings in general graphs and perfect matchings in bipartite graphs. So we can say, what other questions can we ask about signing? This is what we were actually thinking after we proved that the question we wanted to answer was NP-hard. We were saying, okay, what can we solve now? But this is not such a good story. So instead, let's look at the well-known randomized algorithm for bipartite perfect matching. Maybe it's well-known, maybe not, but here's the algorithm by Lovas. It's based on polynomial identity testing, and it goes like that. So now let's recall the signed adjacency matrix, but we have an adjacency matrix of a graph, and instead of signing every edge with either +1 or -1, we just replace every edge entry with an arbitrary variable. Let's call it xij. So xij are real variables that take values over the reals or any field, and we call this the TAT. This is called the TAT matrix of G. So it's just the adjacency matrix where every entry is just replaced by an indeterminate, just a variable. And the requirement is that M is not symmetric now, it's skew symmetric, which means that xij is minus xji. So there is a theorem that says that the determinant of this TAT matrix is not the 0 polynomial, so it's not identically 0, if and only if there exists a perfect matching in G. So this is an old theorem. Here is a way to turn this into a randomized algorithm to test if there is a perfect matching. So, okay, for every ij, arbitrarily and uniformly at random, choose xij from the real numbers. Okay? Then with probability 1, if the polynomial is not identically 0, we would get a non-zero answer, because there is a 0 chance, tending to 0, that you will hit a root of this polynomial if you choose from the whole set of real numbers. The problem with this is that you need infinite randomness to choose from the real numbers, so it's not really something you can do. Instead, there is an algorithm that's successful, and it's based on the polynomial identity testing protocol, or algorithm, I guess. where instead of choosing things from the real numbers, you just have a field, let's call it S. So here you have a polynomial Q on n variables, and I pick n elements uniformly and independently at random from some field S. If I evaluate this polynomial on those random values that I picked and I get 0, I answer the polynomial is identically 0. If I don't get 0, then I know the polynomial is not identically 0. So the question is, what is the probability that I determine that this polynomial is identically 0 when it's not? In other words, what is the probability that this R1 through Rn values are we hit a root of the polynomial after we make our choices from S? And the Schwarz-Zippel lemma says that for a d-degree polynomial and size of field, S, the probability that I get the Q evaluated at R1 through Rn is 0 for a non-zero polynomial is less than or equal to d over S, the degree over the size of where I pick my entries. So now we can use immediately this result, going back to the determinant of a Tat matrix. So this is a polynomial in m variables, 1 for every edge. And it's enough to choose, and the degree is n, right, because it's a determinant. So it's enough to choose a field of size 2n or larger to get probability of error bounded by a half. So I can choose like 100n and get 1 over 100 probability of error. So that's great, and that's known. However, this is still too much randomness. So the natural question is, can I, instead of having to choose xij from a huge field of size n, can I just choose xij to be either +1 or -1? In other words, can I do this by just replacing every entry of the matrix by a variable that's a signing? And here's where signings come in again. Consider the signed adjacency matrix, where now xij's are variables in F2, in the field of 2 elements. And now they're symmetric, not skew-symmetric anymore. It's just the plain old signed adjacency matrix we saw before. So we can show a similar result, that determinant of M is non-zero for all signings, if and only if G has a perfect matching. Which means, yes, I can choose entries at random and independently from only +1 and -1, instead of this huge field of size 2n, and get a non-zero probability of success. Unfortunately, this probability could be exponential small in n, in the number of nodes.
So she's a bipartite matching or regular?
Right now, this is bipartite. I'll tell you the result, the full result, in the next slide. But this is for bipartite for now. So the general result that we have says, take an arbitrary graph G. If the determinant of M, where M is a signed adjacency matrix, is 0 for all possible signings, if and only if the graph doesn't have a perfect 2 matching. So what is a perfect 2 matching? Well, perfect matching is a way to cover the vertices of the graph by choosing edges such that every vertex is covered by one edge. Perfect 2 matching, you can cover the vertices by cycles or edges. So every vertex can be covered by something of degree 2 or of degree 1. And this is just a perfect 2 matching. There might be many of them, but this is an example of a perfect 2 matching in this graph. And the result is in the same flavor. It says that the graph has a perfect 2 matching if and only if there exists a signing that makes the determinant of the signed adjacency matrix non-zero. And you can see it as saying something about non-expanding independent sets. That's why I had this talk sort of title, which I changed later. But this is an old result by I think Tat even, or Lovas or something, one of those people that says that if there is a non-expanding independent set, then there is no perfect 2 matching. So you can translate this result in this language.
That's right. So the complete graph has a perfect 2 matching?
Mm-hmm.
That's obvious.
I mean, it has a perfect matching already, or a Hamiltonian cycle. I mean, yeah. In fact, the complete graph, at least, I think the complete graph has no signing that's 0 determinant. So So it's even like with probability 1, you would get it. Yes.
Okay, so the objective is to minimize the amount of randomness.
Yeah, I mean, there's one of the objectives, yeah.
But there's already non-random numbers for computing.
What's that?
They already exist like polynomial, like non-random.
Yeah, but I mean, this is simpler.
Right.
Yeah, I mean, definitely there exist deterministic algorithms, if that's what you're saying.
Okay, so from what I know, like the point of the approach to using randomness is to like to get parallel algorithms. Like, does this work with parallel algorithms?
I mean, yeah, it would be the same thing. We just use less randomness. The algorithm is identical almost. You just calculate a determinant on a random set of points. So there's no difference, between this algorithm and the other than the fact that it would use much less randomness. And randomness is scarce, so if you want to actually do something, you need as less randomness as possible. This is one of the motivations. It's not even our original motivation, but it's something we've been trying to do, and I'll talk about this on the open questions. Okay, so now here's a surprising bit of information on this. So we saw, let's call this problem invertible signing, given a real symmetric matrix M, verify if there exists a symmetric signing such that the signed matrix is non-singular. This is what I told you before, that this happens if and only if the graph has a perfect 2 matching, which means I have a polynomial-time algorithm to detect whether or not there is a signing that gives you non-zero determinant. So this is not clear a priori. There are exponentially many signings. It's unclear if you can test if there would be one that gives you non-zero determinant. However, it is in P because of this connection with matchings. So now let's consider the other problem, where you have an invertible matrix, and you want to find a signing that makes the matrix singular. This problem is NP-hard. So there's this great disparity between those two problems that, if anything, tells us we don't know much about signings, I guess. Okay, so I don't want to talk about any more technical details, but I do want to focus on a few open questions that arise from this work. If you have any ideas or or any suggestions, that would be welcome. So the one thing is that we know how to find a perfect 2 matching. However, we don't know how to find a signing that's non-singular. So this problem, we don't know if it's in P. In fact, it is along the flavor of problems that there exists a solution, but then finding it is something that's PPAD or PLS complete. So there are these game theory classes, I guess, motivated by game theory, that are, have an exponential search space, and there's always a solution. The question is, can you find it in polynomial time? So like Nash equilibrium or Spenner's lemma, et cetera, et cetera. There are a lot of PPAD complete problems. We conjecture, or maybe, I don't know, we don't even know if we conjecture that, but it would be an interesting direction to show whether or not this problem is complete for one of those classes. For those of you who study the theory of polynomials, this question is similar as asking, saying that a d-degree polynomial cannot have more than d+1 roots. So in fact, it says that if you have a set of d+1 elements, there is one that evaluates to non-zero for a polynomial that's not identically 0. So the multivariate version of this is very close to the signing question. Find a signing whose determinant is not 0, because determinant is a polynomial. So you can kind of see through the non-Stellanza multivariate polynomial non-Stellanza kind of light. They're different problems, but maybe they're both PPA, PPAD, something complete, something along those lines.
So how to do it in the bipartite case? Like a bipartite graph with a perfect matching, you know how to find a non-singular sign? Okay.
In any case, yeah.
Sorry. So if the graph had the perfect matching, did you already explain how to find a non-singular signing?
We don't know. I'm saying that.
No, just a matching, not a 2 matching.
Yeah, we don't know. I mean, if a bipartite graph has a perfect matching, it will also have a cycle, a matching, because you'll connect the matching edges they have to. right? So if it has a perfect matching, it would have a perfect 2 match. No, sorry, that's not true. What I just said could just be a disconnected graph. But yeah, okay, I was thinking about something else. Sorry. But yeah, no, we don't know how to do it in the general case when the graph is bipartite and it has a perfect matching. We also don't know if this problem is in P in that case. So it could still be complete for some class, even if we restrict our attention to bipartite graphs.
And the graph having a perfect matching, not even a 2 match. I mean.
Yeah, I mean in bipartite graphs, perfect matching is a perfect 2 matching. So by definition, a perfect 2 matching is a potential cover of the vertices, bicycles, or matching edges. But if you just have matching edges, this is still a perfect 2 matching.
But I'm restricting the graph.
Yeah, we don't know how to find the signing. Yeah. So the other question that relates to the randomness needed for this bipartite matching algorithm, to work, is what fraction of signings. If I take a graph that has a perfect matching or a perfect 2 matching for general graphs, what fraction of the signings are singular and what fraction are non-singular? If there is a whole lot of signings that are non-singular, then a random algorithm is great, because I have a constant probability of success. However, as I mentioned before, there are graphs like a disjoint union of 4 cycles, for example, that have exponentially small fraction of non-singular signings. So we have exponentially small probability of success, when we evaluate this determinant polynomial in a random point. However, maybe those graphs with exponentially small fraction of signings have a characterization. Maybe they're not well connected, or maybe they're not expanders, or maybe we don't know what characterization. So finding a characterization of graphs where the fraction is low or high or in the middle is an interesting problem I think it's an interesting problem. And an idea we had about this, and it might not even work, is that instead of signing now the adjacency matrix by +1, -1, you could sign it by roots of unity, or you could sign it by but something that looks like roots of unity. So use larger lifts. This corresponds to using lifts of larger k in this lifting process. Can we improve upon the fraction of non-singular roots of unity signings or larger signings if we use complex roots of unity, for example, or something like that? And then if we could do all those things, then we would indeed reduce the randomness in the matching algorithm by a lot. Okay, so I'm done. Thank you. Any questions? Yes.
So for the larger list, is there like a corresponding way to define like a signing matrix? Would you use if you use larger roots of unity, wouldn't you only get like cyclic shifts in that sense?
Yeah, so we want to use cyclic shifts for this approach, but then there are K matrices where K is the size of the lift.
Yeah. And so I'm also sort of wondering, is there a way, so say I don't care just about cyclic lists, I care about every possible,
this becomes harder. So the matrices so you have a bunch of matrices, the union of their spectrum is the spectrum of the adjacent matrix of the lift. If you take cyclic lifts, they are K matrices, and you take the union of their spectrum, and you get the spectrum of the lift. If you take non-abelian groups, then it depends on the representation theory of the non-abelian group. So you could get 2 matrices, or you could get any number between 2 and K. It really depends on the representation theory, how many reducible representations you have, and then for each of the representations you have a choice of basis, so it becomes very, very complicated to analyze those.
CSS developed, I don't remember the part as well, a lot of interesting technology for this work. Were you able to use any of that? Interlacing polynomials and. It seems like there was a lot of stuff that.
Not for this. We have tried to use it to construct expanders, but we haven't succeeded. So, yeah, I've been using it, but not with any significant success. along those constructive lines. There is a person that used it successfully, somewhat. Mike Cohen, I think, from MIT. He's a student who constructed Ramanujan multigraphs that like approximate the coefficients of the polynomials, of the determinant polynomial and stuff. But we haven't been able to use it successfully. Yes.
So you're going to answer the question about approximating a graph with positive and negative weight edges and partitioning it? Remember the original, you said somehow that you would think of negative weight edges as a repulsion,
Yeah.
you know, or a dislike.
Yeah, I mean,
And then
but
there
there's
should be
no correlation between this and partitioning in some sense. I mean, there is some correlation in the sense that if the largest eigenvalue of the sign matrix is D, then you have an extra disconnected component, right? So you can say something, but Cheeger's inequality in nature looks at the sparsest cut. And since the eigenvalues of the original graph live there, you cannot get away from the sparsest cut of the original graph. So now if you impose that the original graph is an expander, then yes, the lift eigenvalues tell you something, but if it's not an expander, then it becomes very complicated. So yes and no, but there's no direct correlation. It depends on what the base graph does, pretty much. Yes.
So in your application to sort of non-bipartite graphs, you can say there's a signing upon which the mononomial value is just something non-zero, if only if it has a 2 matching. What if I really sort of want like a matching, like I'm not going to accept cycles at all? Can you still,
No.
Is that false, or you actually verify that's false? Or
For this is, I think it's false,
so I
but
could have I could have like a graph with the perfect matching, but every possible signing will evaluate.
no, a perfect matching is also a perfect 2 matching.
Oh,
Is that your graph?
oh, that's true. Sorry, yeah. So I get the opposite.
So
yeah,
no,
so,
yeah.
So yeah, but should I?
But it's not true that if there is,
Yeah.
it's not true that if there is one that gives you non-zero, then there is
Yeah.
a perfect matching.
Yeah.
There could just be a perfect 2 matching.
I see.
Like for example, you can take an odd cycle or something like that, and then there would be a Hamiltonian cycle. So this, but there would not be a perfect match, right? So if you wanted to only have matching edges, there is no perfect matching, but there is a perfect 2 matching, and you still get a non-zero signing.
So with the positive negative weight edges, though, you can probably use Leighton-Rao or ARB for that or not? Does that work?
I haven't thought about cutting the sign that,
Well, just that you brought it up and it seemed like a very nice question. I was just curious whether maybe other technology does work.
so I think not, because, this is where we started from, actually. The first time I ever thought about signing was because of the unigames projection, which is still very relevant at the moment, but we were proving that if the graph is an expander, then you can solve unigames, approximate unigames in polynomial time. And the way to do that roughly is that you take a lift, which corresponds to the labeled extended graph of the instance, and you look at the sparse cuts in the lift. If the original graph was an expander, the sparse cuts are assignments. So they correspond to assignments. But you can't do this in general. So if the graph was not an expander to begin with, if you were able to do what you're saying, then you'd be able to solve unigames. Not exactly, but roughly. It would have implications that I don't think can happen. Okay, thank you.
Thank you.